In assignment D6, we're going to discuss asymptotes and curve sketching. So the learning outcomes for this lesson are, upon the completion of this workbook assignment, we should be able to use a function's graph to determine any horizontal and vertical asymptotes, use a formula for a function to evaluate limits, one-sided or two-sided algebraically, use key properties of essential functions such as absolute value, sine, cosine, e to the x. For example, sines, periodicity, domain, range, and behaviors, using appropriate reasoning about infinity and or zero, identify discontinuities by type and justify the using the definition of continuity, predict a function's vertical and horizontal asymptotes, if any, using limits, and justify your answers by checking zeros or leading coefficients is not enough. So some of you may have seen these limits before. So there are some indicators in the function that might lead you to what the final answer to the limit is, but that is not formal justification of how you arrived at that answer. So we will go over that today in our guided examples. So the advice for mastering the learning outcomes, for horizontal asymptotes, we say that the limit as x goes to positive infinity of f of x equals L if the values of f of x, remember limits are trending of the y values, approach the number L as x increases without bound. So in this situation, we would say that the line y equals L is a horizontal asymptote for the graph. So let's actually sketch a scenario of what's going on here. So I'm going to draw a function, and this function is going to have an horizontal asymptote at some value L on the graph. So we typically sketch the line as a dotted line when we have a horizontal or vertical asymptote. And the line is not part of the graph, it's just a guideline of how the graph behaves near that value. So if I have a function f of x, this says as x approaches positive infinity. So positive infinity is the right side of our graph. And the line has to approach L, or the graph, excuse me, is going to approach this line L but never cross it on the right side. So this is what a graph f of x with a horizontal asymptote at y equals L might look like. There are a couple different variations. But what we want to make sure we understand about this notation is that as x approaches positive infinity, what we are doing is we are checking the behavior of the right side of the graph. So notice here that it says as x goes to positive infinity. This horizontal asymptote is only the behavior of the right edge of the graph. If I want to know what's happening on the left side of the graph, I would have to check the left edge of the domain or look at how the graph behaves as you go out to x equals negative infinity. If we say the limit as x approaches negative infinity equals L for some value L, then x is what we say decreasing without bound. It means it's moving toward negative infinity. And in that situation, we would also call y equals L a horizontal asymptote. So let's sketch a picture of what this would look like. So this is a graph whose left edge is approaching some value L. So I'm going to draw an asymptote. And this means that whatever function f of x, however it's behaving, as x approaches negative infinity, the graph approaches this line L off to its left edge. So we can say that as x approaches negative infinity, we are checking the behavior of the left side of the graph. So if a function, if we check the right side and let's say the limit is 2 and the left side, the limit is 3, you actually can have two horizontal asymptotes. One only explains the behavior on the right side of the graph while the other explains the behavior on the left side of the graph. Sometimes those are the same value. But similarly, if we evaluate a limit to infinity, meaning we're looking at the right edge and it works out to be positive infinity, then we say that function is increasing without bound as x increases without bound. So the word without bound is a way of saying infinity in words. But if the limit to positive infinity equals negative infinity, then we would say the y values are decreasing without bound. So in both of these instances, we are looking at the right edge of the graph. So let's draw a scenario where this is true. So I'm going to sketch two pictures. And over here, I'm going to show you what a graph as on the, where the right side approaches positive infinity. So this is the graph of e to the x. And we can see that the limit as x approaches positive infinity of f of x equals positive infinity. So as we look toward the right edge of the graph, the y values are blowing up to infinity. But if I sketch a graph like this, well, now as I check the right edge of the graph, I can see that the y values are decreasing without bound, and so the limit as you go to positive infinity is negative infinity. So it can happen that you have two infinities, right, in the expression, but remember this is telling you whether you're looking to the right or to the left on the graph. This is describing the behavior of the y values, how they are trending at that particular location. There are a couple of important facts we're going to invoke today when we're working on problems. The first is powers. So if we take the limit as x goes to positive infinity of 1 over x to the r, where r is positive. So this could be 1 over x squared, 1 over x cubed. The limit of this will equal 0. And similarly, if we take the limit as we go to negative infinity of x to the r, where r still needs to be positive, then it will also equal 0. The reason r needs to be positive is because if r is negative, then this equation could be rewritten where x to the r could be put in the numerator, and then this thing would not equal 0 anymore. So 1 over x to any power, as long as that power is positive, we get 0. E to the x has some special behavior around infinity as well. So this is actually a good representation of the graph of e to the x. So we can see that if you check the right edge of this graph, it equals positive infinity. If we look at negative infinity of e to the x, we can see that the values are approaching 0. But now, if I take e to the negative x, well, e to the negative x takes this picture and flips it over the y-axis. So now it would go up to positive infinity on its left side, and it would go to 0 on its right side. So it just takes this picture and flips it backwards. So that's why these values appear to switch places in each of these. Another important fact that we're going to look at today is that the absolute value of x is equal to the square root of x squared for every possible value of x. So this is a little bit strange to wrap your head around if this is the first time you're seeing this, but if you graph these two functions on the same graph, they lay right over each other. The domain of each of these functions is all real numbers. because any value you plug into the square root of x, because the x is being squared, all of the things that come out of here are going to be positive, and then you're going to invoke the square root. So this will actually accept all real numbers as well. The square root of x squared, if x is positive, right, is going to give you just a positive value, but we could also have to account for all the negative values that we would get as well. So here is what the graph actually looks like. So this is the graph of f of x equals the square root of x squared. And it is the same graph as f of x equals the absolute value of x. Now another thing we want to make sure that we understand is when this comes up in an equation, we need to see from our picture here that the absolute value of x, remember, is the line y equals x to the right of 0, and it's the line y equals negative x to the left of 0. We will see that same behavior represented when we look at some limits. The last thing that I want to mention before we start working problems is that you cannot evaluate infinite limits. So what we mean by infinite limits are limits where x is going to infinity. So you cannot do this with direct substitution. So that's why we need these important facts. You can't just plug infinity into things and see what happens. So we need to make sure that we have some facts and some things we can invoke to help get us out of some pickles that we might find ourselves in these guided exercises.